All right, hello, welcome back to Chapter 16, Part 3. We're talking about stream load, and I apologize for the hair. One of these days I'll get a haircut or shave it off, who knows. Anyway, stream load. We're talking about the material that is eroded into the stream that is carried away, right? So they call that hydraulic action. That's just simply a fancy term for the water moving rock fragments and moving them. So I think it's like if you're doing dishes, right? And you've got junk stuck to your plate and you put it under the faucet or the sprayer and that pushes it away. That is hydraulic action. Okay. Now, when these materials are in the water, specifically like rocks and large chunks, they bump against each other and they roll around and they're moving, and they can actually take rocks that have sharp edges and polish them or break them down and almost give them this kind of this finished look. Okay, anything that is moving in the water, so dirt, rocks, trees, anything, sewage, rubber gloves, is actually called the stream load. That's what's in the stream. Okay, and the size of these particles, it depends on a couple things. If there's more water or if it's moving faster. So stream discharge, right? How much water is in the stream and how fast is it flowing? So if you want to, really blast your dishes clean, what do? You turn up the water pressure, right? So this is actually what happens. This is a river that flows in the Himalayan mountains. That's my son in the background talking about lunch because it's important that we all eat our lunch. These rocks you can see here, all kind of rounded. They've come down the stream from the mountains. They've hit each other, kind of bumped each other, knocked the sharp edges off, and they have that kind of look. Stream abrasion, stream rounding. So when we look at things that are in the water, the stream load, we can break that down into three main types. The first one is the dissolved load. These are things that dissolve in the water like chemicals. So salt can be a rock, but when this is exposed to water, it actually dissolves and becomes sodium chloride in the water. Limestone is a rock, but given enough time, it will dissolve into carbon calcinate. So these are things that are in the water that you necessarily can't see. Next thing is suspended load. So these are things that maybe are too small to see individual, but they don't dissolve. They just kind of float in the water. So much like dust in the air kind of hangs in the air, you can have dust or dirt in the water. So that's why some water looks brown or muddy. It's that actual sediment. And then the last one is the bed load. And these are the things that are too big to either dissolve or be suspended. So large rocks or trees, and they kind of just either come in the current. Now, different waters, based on where they're flowing from, can have different suspended loads. You can see right here these two rivers, the Drava and the Danube, they meet right here. But the Danube flows through an area where there's a lot more fine-grained sediment in the dirt. So it's much more brown looking, whereas the Drava does not. And you can see this mixture right here. So how does the bed load move then? Because the bed load, remember, this is the stuff that's too big to dissolve. So just like in the sand, right? We'll talk about this. The sand grains move along the bottom. They kind of hop or bounce as they're pushed along, and they call that saltation, right? So remember, the dissolved load are the minerals that we can't see, like salt. The suspended load is the silt and clay that kind of gives it that muddy look. But the bed load, right? They kind of either bounce along the bottom, that's saltation, or if they're too big to do that, they kind of just roll, getting pushed along. That's called traction. Now, the size of those fragments that the stream can move, they call that the stream competence. So a stream that has a higher competence can move bigger items and more of them, whereas a smaller stream cannot. Stream capacity is if you add up all the material that is not water in the water. So dust, dirt, chemicals, trees, rubber gloves, whatever's in there. And the capacity. As a stream increases its discharge, it has more water, the capacity goes up. It has more water to carry things. And if the speed of the water increases, which usually happens when you have more water, the stream competence also increases. So again, let's go back to that analogy of dishes, right? If you're washing off your dishes in the sink, you've got just a little tiny trickle of water going, you really can't do much with it. But if you turn up the water to full pressure, right, now you've increased the discharge. So now you can wash off bigger things and flush them further away. And that's the same thing with a river. Now, another thing that can adjust this, besides the amount of water in the river, is the gradient. In other words, what is it flowing down? Streams start usually in high elevations and flow down by gravity downhill. But what if the hill is steep? The water will flow faster. So the Chicago River, the gradient is very, very low. It doesn't have a very strong current. But if you go to northern Wisconsin, there are rapids where they flow down from a much higher elevation. If you go to the mountains, you see whitewater rapids. So those are called high gradient streams. In other words, from where they start high to low is shorter. So they have a steeper gradient. Okay? Low gradient streams are almost flat and have almost no current. So it looks kind of like this. And in fact, a river or a stream can actually have multiple gradients along its profile. So up here where it starts, right, in the mountains, it's very steep. So here at section A, right, very steep gradient. Here in section B, the gradient's a little bit less. And when we get to section C, it's very flat. So the water would flow fastest at A and the slowest at C. And we're going to talk about this. One of the things that happens is the profile here shows you that the faster the water goes, the different types of streams it carves. Let's talk about that. So the base level. When water is flowing, it eventually goes as low as it's going to go. It reaches the ocean. That's base level. What's the lowest the water can go? The water can't flow any more downhill. It's usually sea level. The Mississippi River flows from Minnesota all the way down to the Gulf of Mexico. That's sea level, right? The Grand Canyon starts in the Rocky Mountains and ends up in the Pacific Ocean eventually. So that's base level. Now, what type of canyon or valley or riverbed does the river carve? It depends in large part on the topography. So in other words, how high does it start? If a stream starts really high in the mountains, it has a longer distance to go down. That gives it more power, right? It's like picking up a big heavy bag of flour. If you drop it from maybe your first floor as opposed to dropping it from your third floor, right? The further it falls, the more energy it has. The other thing, the stream discharge. How much water is in the stream? How big is it? How much water does it have? Also, how fast does it flow? And then the last thing is the land that it flows over. What is the rock like? Some rock is harder than others. What if there's more dirt on top of the rock? All those things affect how valleys and canyons are carved. So let me show you some examples. In a V-shaped valley, what you have here, the rock and the soil is pretty soft, so the water has an easy time cutting through it. And as the water cuts down deeper into the rock, more rock falls into it. So you get this kind of broad V-shaped valley. But oftentimes in mountainous areas where the rock's much harder, you get this almost slot with almost straight edges. There's a lot of these actually in Idaho, very hard rock. And what happens is as the water erodes down, the rock stays pretty much the same shape. So you get these narrow slots. Now once in a while it's kind of interesting. You'll have a layer of soft rock in between here. And when the water gets down here, it can actually undercut like this, and the sides will collapse. The Grand Canyon is interesting because it has layers of hard and soft rock. And so if you have a layer of hard rock, you get that kind of slot look right here at the top. But then here's a layer of soft rock. Now it's kind of shallow, and it goes back and forth, almost like stair steps. Now, a nick point is a fancy name for basically a cliff. It's any location on the river where its gradient increases rapidly over a short distance. In other words, it's flowing downhill at a steady pace, and then it goes downhill really fast in a short period of time. So a waterfall or rapids. In fact, all waterfalls form at nick points. Okay. Now another name for this also is escarpment, which is just a scientific name for a long row of cliffs. And so when you're looking at a cliff, right? If you're looking at the top, you're looking down, but the face of it, right, is the escarpment. And water flows over an escarpment at a nick point. When it does fall down, right, what happens is the water flows down over the cliff. When it hits the bottom, it forms what's called a plunge pool. Let me show you what that looks like. So here, water's flowing. Here's the nick point. It flows over this escarpment, over this cliff. And when it hits right here, all the action of the water breaks up this rock. So it forms this kind of deeper little pool called a plunge pool. And all these rocks get moved around. But what's often interesting at waterfalls is usually this is very hard rock. It doesn't erode very well. But underneath, you might have softer rock. So as the water falls over and these rocks are basically pummeled around, it erodes this rock faster. And underneath or behind the waterfall, the face of the cliff can go back further, further, further. If this keeps happening over time, this top part becomes unsupported and snaps off. And what happens is, over time, it looks like the waterfall is actually moving. The cliff's moving backwards. And that's the erosion of the water. You can see right here, Niagara Falls. Here's the line of the falls, and here's the cliff front right here, where my cursor is. But over here, it started to kind of cut a little loop right here. Niagara Falls is interesting because actually Niagara Falls is in between Lake Erie and Lake Ontario. And between the two lakes is a roughly 30-mile strip of land, and the Niagara River flows from one lake to the other. And over the last 10,000 years, Niagara Falls has actually moved up the river about 7 miles, which means that in about another 20,000 years, it'll actually go all the way up the river into the other lake and will disappear. So once we're out of the coronavirus situation, I definitely recommend going to Niagara Falls because in 20,000 years, it'll be gone. So you better get in and see it now. All right, we're going to pause right here for commercial identification. I'll come back with part 4 after I eat my lunch and comb my hair in just a minute.